Hello AP Calc class. We're going to look at the notes for section 2.4 entitled Advanced Differentiation Techniques, and the main thing that we're looking at in here is the chain rule. On the second part of this video, we're also going to look at doing some derivatives of some of the other trig functions and also the natural log and common log functions, and those are called the transcendental functions. Just sometimes you'll see that in the book, they call them transcendentals. Okay, so to introduce this chain rule, so what we know so far for rules, we have just our general power rule, which is multiplying the exponent down and then reducing the power by 1, and then we have our product and our quotient rules. So those are the rules we've looked at so far. Now those will now be combined with what's called the chain rule. So it says the best way to introduce this new differentiating technique is to show you types of functions that would require its use. So the table below illustrates pairs of similar functions that can be differentiated with and without the chain rule. So on the left side, these are functions that do not require the chain rule. Over on the right side, these ones do require the chain rule. Now, the thing that hopefully we're going to notice here on this right side is that what we have is we call them a composite function. Like you have one function within another function. So for example, here we have a square root. Inside of that, we have a quadratic function. So when we see that happening, when we have one function inside of another one, that's when the chain rule is going to be required. So I'm going to talk a lot about the inner function and the outer function and how we differentiate when those are combined together as a composite. Now here, this one may not seem like it as much just because you're like, well, there's not. A lot of times what I say is if there's parentheses, that'll give it away, but sometimes parentheses are more implied, like here. We'd have parentheses here. Technically, we're taking the sine of 6x, and so, the outer function is the sine and the inner function is the 6x, right? Here, this is a little clearer. I think the outer function is the 5th power and the inner is the 3x plus 2. And again, here we've got the outer function is tangent and then the inner function is x squared. Okay, and whereas here, if it's just, like we're taking tangent of just x, as long as it's just x, then we don't have to really think about the chain rule, and we'll talk more about that later. Okay, so basically, this is what it is. I kind of like their function notation instead of the dy dx notation. We can talk about both of them, but it shows more easily, I think, that there's an outer function. The f function is the outer function and the g is the inner function. And so when we apply this chain rule, we do the derivative of the outer function and leave the inner function alone. But then what we have to do is we have to multiply by the derivative of the inner function as well. So what we're going to do here is we're just going to identify, what is this would be considered our inner function here, the u piece. So they're calling that the g of x, which is kind of that inner part. So this would be like our inner function. And then the f of, that expression is going to be the outer. That would be our outer piece. Okay. So as we're identifying these, so I would say like u in this case would just be that x plus 1, which is, the part that's in the bottom, because there are really kind of two things here. And like I said, there isn't always parentheses, but we could think of that part in parentheses, and that's like my u piece, or the inner piece, okay? And then the outer is that rational function piece, which is 1 over something. So like y equals 1 over u would be kind of my outer piece there, right? In this one, the u would be the inner part, and again, it's that part in here, which is the 2x. And then the outer would be the sine of whatever it was, in this case 2x, but we'll just keep it in terms of u because that's the way we're kind of showing it here. This next one, we'd say u is equal to the inner part, which is this right here, 3x squared minus x plus 1, and then the outer would be that square root function, which is square root of something, which we'll just call it u. And then finally, u in this case would be the tangent of x, and the outer piece would be the squaring piece, because really this means, when they have it written in this form, it means tangent of x, and then find that value, then square it afterwards. We write it like this as more of a shorter notation, which means this, to eliminate having to write parentheses. So the outer piece here would be, that's something squared, which in this case tangent of x squared. Okay, I want to run you through a pretty basic example of applying the chain rule. So hopefully you can see in this one, the inner function is the x squared plus 1. The outer function is the cubed, the third power, okay? So the first thing that we do is we apply the derivative to the outer function. Now because it's a power of 3, that gets multiplied down. So the 3 gets multiplied down in front. This piece stays the same, okay? And then what happens is we reduce our power by 1, right? And that's, we've been doing that. Like if I just had x to the third, I know that that's how that works. I multiply the 3 down, and then I reduce my power, and then I'm done. But this is a little different from what we have here, because in here we just have an x. Here we have something else. We have another function. We have x squared plus 1. Okay, so according to the chain rule, if you have something else here other than just x, now you have to multiply by the derivative of that something. And so I multiply by the derivative of the x squared plus 1, which is 2x. Okay, so let me refer back here. Okay, so that's what we're doing. So I did the derivative of the outer piece, the outer piece being the cubic part, so that's that f prime. And then I left the inner piece alone. I left that as x squared plus 1. But I have to multiply by the derivative of that inner piece afterward. Okay, so that's called the chain rule. And to simplify a little bit, we probably take the 2x times that 3. So I'd have 6x times x squared plus 1 squared. And that would be my derivative of this function y. Okay, that's the basics of the chain rule. Derivative of the outer piece, leave the inner piece, and then multiply by the derivative of the inner piece. Okay, and that's really the shortcut that I just showed you here. We're going to apply that, power rule right there, and then multiply by the derivative of the u or whatever that is inside. Okay, or another way, u to the n, multiply the n down, reduce the power, multiply by the derivative of the base, whatever that u is, and it's going to be something like this, x squared plus 1, or usually some kind of polynomial many times. Okay, so here, if you think you got it, you could try these, pause it and try them. I'm just going to keep working through. So if we take the power down, just like it tells us to do here, right, or here, we're going to multiply that power down, so we'd have 3 in front, and then we'd leave the 3x minus 2x squared in there, and we reduce that power down to 2, and then we multiply by the derivative of the inner piece, which would be 3 and minus 4x, just like that. Okay, now could you simplify it more? I suppose you could square this out, but I would probably just leave it like this, given the choice. You don't really have to do any more simplifying than this. Call this dy dx. Sometimes, if you're matching it with a multiple choice and your answer doesn't look like the choices, like none of them, then maybe you have to do a little more simplifying. Okay, now something like this where you have a radical expression, it's easiest to apply any of these power rules, and the chain rule usually involves some power rules. It's easiest to write it as, fraction exponents or rational exponents. So I would rewrite this as x squared minus 1 squared, that's my inner piece, and then it's the cube root of that. Now a cube root really means a 1/3 power. And by writing it like this, I actually can simplify it before I start, because now what I would do is I would multiply a power to a power. The rule for that is to multiply those. So I have x squared minus 1, and then that's going to be to the 2/3 power. Now, I haven't done any derivatives yet. All I'm doing is just rewriting this expression in a way that makes it friendly for doing the derivative. Okay, so I've got y equals x squared minus 1 to the 2/3 power. That's just rewriting it. Now I'm ready to try to find the derivative of that. So I'm going to bring my power down, so I'll have 2/3 in front, and then x squared minus 1, and then I have to take 1 away from 2/3. Now 2/3 is less than 1, so when I subtract 1 from it, I'm going to get a negative exponent. I'm going to get negative 1/3, right? And then I have to apply my chain rule now. So I did the derivative of the outer part, the 2/3 power. Now I have to do the derivative of the inner part and multiply by a derivative of x squared minus 1, which is going to be times 2x there. Okay. Now, I would say on something like this, you're never going to see a choice where they leave it looking like this with negative exponents. So, remember with a negative exponent, what we do with that is we drop it down into the denominator and give it a positive exponent, right? So let's rewrite this. So the 2/3, I'm going to leave the 2 on top and the 3 on the bottom. And then the x squared minus 1 had a negative exponent, so if I drop it down to the bottom, I can say now that's to the positive 1/3. And then on top, that's going to be times this 2x that was here, right? Times 2x. I'm going to clean this up some more, but that's, hopefully we can see that this piece here had to go down into the denominator because it had a negative exponent. The 3 was already in the denominator, so I'm going to leave that. The 2x is times that 2. Okay, so cleaning that up, I'd have 4x on top, and then I'd have 3, and they'd probably go back to a cube root instead of a 1/3 power. Cube root of x squared minus 1. It's probably the most likely way you'd see that answered. If it starts with a radical notation, it'll probably end with that again. So, okay, so hopefully that one is making sense. And let's do one more here. So this one, it is set up as a quotient. If I just have a constant in either the numerator or the denominator, to me it would be easier to just rewrite this, I think, as a product, because if this whole thing in the denominator is to the second power, I could just say that it's 2x minus 3 to the negative 2, right? So I could start off by rewriting it like this, and then I don't really even have to do a power or a quotient rule here. I need to do I don't have to do a product or a quotient rule. I just do my power rule here. So I'm going to multiply that 2. So when I do my derivative now, the outer function is the negative 2 power, the inner function is the 2x minus 3. And this is just a constant in front, so when I multiply, I can just multiply negative 7 and negative 2 and get positive 14. And then I'll have 2x minus 3, and then I'll take 1 away from this power, so that'll be to the negative 3. But I have to remember, because that whatever is in here, I have to do the derivative of that. So that means I have to multiply by the derivative of that, which is just 2, right? And so I'm going to take 2 times 14 and get 28. So I'll have 28 times 2x minus 3, the negative 3. And again, I think we want to get rid of that negative exponent. So let's leave the 28 on top, and let's put the 2x minus 3 to the third power on the bottom. So that's my dy dx. All right. We got a few more. These ones, it says nested product and quotient, product or quotient and chain rules. So what they mean is, many times it starts off as either a product or a quotient. Like this starts off as a product rule, but inside of that product, when I do the derivative of the second piece, there's a chain rule involved there, because we have this 1 minus x squared is an inner function inside of a square root. So these get to be, you gotta keep your thoughts straight as you're doing it. You gotta apply a product rule, but when you do the derivative of the second piece, there's a chain rule involved there. Okay, so let's see what we can do with this one. So f prime. So derivative of the first is going to be 2x, and then we leave the second part alone, so the square root of 1 minus x squared. Plus, now this is my product rule, right? Derivative of the first times the second plus the first times the derivative of the second. Now, derivative of the second, maybe it'd be helpful, like before we started, if I would have written to the 1/2 power, maybe, I don't know, just to help you think about how we're going to do that derivative. So, the square root of that is like to the 1/2 power, right? So the first times the derivative of the second, so I'm going to bring that 1/2 down, so I'm doing the derivative of this thing right here. So I'd have times, and I'd have 1/2, and then 1 minus x. Now that's going to be to the negative 1/2 power, right? And then I have to go, sorry, that's squared there too. And then I have to do the derivative of the 1 minus x squared and multiply by that, which is just going to be negative 2x. Okay, so derivative of the first times the second, that was easy. But then when I did the first times the derivative of the second piece involved this chain rule here. Okay, now I want to clean this up a bit. So this part really can't do anything with that. But I've got negative 2x times x squared times 1/2. So that's going to be negative, x cubed, right? The 1/2 and the 2 cancel. And then I end up with x cubed, and it'd be negative x cubed. And then this piece, I think, since it's a negative exponent, let's put it on the bottom. Probably put it back into a square root. 1 minus x squared. That's most likely the way you would see this answer. That's what I would think. They'd probably leave it looking something like that. Okay, let's make sure I didn't miss anything here. I think that looks good. Okay. All right. And there are a couple more here, and just for time's sake, I'm just going to talk through these ones so that we can go a little bit faster here. So here we have a quotient, right? Now again with this, what you could do is you could write it as a product. I think that's probably easier in this case. So because it was x over, this is technically x over x squared plus 4 to the 1/3. So what I can do is I can rewrite it like this, right? I can bring this up to the numerator and call it to the negative 1/3. Now I've got a product there. I think that's a little easier to deal with. So when I do this product rule, I am going to have a chain rule to use on that second piece. So derivative of the first, which is 1 times the second. That's this. So technically, my derivative of the first was just 1 times that stuff, right? And then plus the first times the derivative of the second. Now, this is the first, the x is the first. Derivative of the second, multiply the power down, negative 1/3, and then the x squared plus 4 stays the same. Take 1 away from negative 1/3, right? So negative 1/3 minus 1, or minus 3/3 is negative 4/3, right? So that's where I get that from. So that becomes that. And then times the derivative of the inner piece, which is times 2x. All right, so now we kind of clean this up again. We've got, this I'm just going to say 1 over the cube root of x squared plus 4. Up here I'm going to have, 2x times this x, which is 2x squared. This 3 I'm going to leave down in the bottom. And I'm saying minus here because this is negative, and so I was going to say that's going to change this plus sign to a minus sign. And then I've got x squared plus 4 to the negative 4/3. And hopefully you remember, if I have a 4/3 power, that means that the root index is a 3 and then the power is a 4. Now because it was negative, that's why I'm dropping it down here. And so I've got 4/3 power like this, and then the x squared plus 4 stays inside. Okay, so you really do have to know your algebra rules when you're doing calculus. It's implied that you kind of remember all this stuff. So ask questions if you're struggling with any of that. Okay, and then the last one, I think we have to use I don't see any real easy way to get around the quotient rule in this one. So I think we'll have to use a quotient rule here, but the outer piece is going to be this, it's going to be the squaring function, right? So I'm going to apply that first. So I take 2, multiply it down, and then I reduce that down to the first power, which I didn't write, but obviously first power is, you don't have to put that in there. But then when I do my chain part of this, the derivative of the inner, I end up having to do a quotient rule here, right? So quotient rule, let's talk through that one again. So it's low d high, so that's derivative of the top times the bottom, right there, low d high, minus high d low, so that's 3x minus 1. Derivative of low is just going to be 2x, and then all over the square of what's below. So we're squaring x squared plus 3, and so that's how that ends up. Now when I simplify this, up top here, I could distribute the 2x through there, and I could distribute the minus sign, and so I end up with, I distribute this 3 here as well, 3x squared plus 9, and then that would be minus 6x squared and plus 2x. Okay. And so that's what I would get by distributing that stuff. And then there isn't, I guess if I do that, I think I would probably just leave these all as factors then. So when I combine any terms here, I can combine the negative 6x squared and then 3x squared, and that's why I have negative 3x squared there. Plus 2x, that stays plus 2x, and then plus 9. Okay, and that's pretty much it. And then down here, I have x squared plus 3 squared, and then I have x squared plus 3 to the first here, and so that's why I'm putting cubed on x. When I multiply those together, that would just raise that power by 1. So this is probably the best way to leave that answer. Okay, so that's all I'm going to do for this video, and then we'll finish examples 7 through 10 in the next video.